The R32V2020 RISC CPU puts all of the peripheral devices together, both internal and external peripheral devices, into a peripheral interface piece of VHDL code. That code is accessed by address, control, chip selects, and it has all of the connections to the external pins on the device, as well as keeps track of the internal signals that are used for peripheral access. Let's take a look at some of the peripherals. The card that we're using has 8 individual LEDs, so there's a latch for those 8 LEDs. The card also has a ring of LEDs with 4 edges with 3 LEDs on each edge, so there's a register for that as well. There's a buzzer control circuit that controls the frequency put to the buzzer. In this case, the card has an actual buzzer, so this doesn't work well on this card. It would just need a voltage applied and it will only create a single tone. But on some of the other cards, the buzzer is more of a little speaker, so varying the frequency will produce different tones and notes. There's VHDL code for PS2 keyboard and the logic to convert those key codes from the keyboard into ASCII, which can be understood by programs. Some of the cards have 4 7-segment LEDs and some have 8. I've got 2 different modules here. This one is for the 8-segment display, and it latches the data so that it can be written from the CPU. That can be useful with the timer units or any sort of output that you want to see on the screen or on the 7-segment LEDs. It's particularly useful for debug. One of the more powerful features of this is a VGA adapter. In this case, it's set up for 1024 by 768 video, and that corresponds in mapping to 64 characters per line by 32 rows of characters. And that interface is memory mapped, so to write to a character on the screen, you write a byte to that particular address. This allows for very, very quick operation. Screen clears take something like 4 milliseconds, which is 4 times faster than the screen itself is actually being scanned by the 60 Hertz video. So it's really, really, really fast. There's a timer unit as well that contains multiple timers. One of the timers is the ticks of the CPU or the clock, which is a 50 megahertz clock, so it's a 20 nanosecond tick. There's also a microsecond timer that can be read and then checked again later repeatedly until a particular count is reached. There's the same thing as a millisecond counter. I've also put in place a CPU cycle counter that for every transition through all the cycles of the CPU it increments by 1, which could also be used for counting CPU clock ticks. And the final peripheral unit here is the buffered UART, which is used to connect out to the USB to serial interface, in this case hooked up to my PC as the host. And when we run the code, we get the result that it takes 5 milliseconds to clear the screen. If we wanted a more precise number, because the error here is about a millisecond, it could be off in sampling that clock. If we wanted a more accurate or precise result, we could use the microsecond counter. Now the counter results are all printed in hex, so you'd probably have to convert that to decimal if you wanted a number you're more comfortable with. So you can see this design is more than just the RISC CPU, it is also a system on a chip. If you want more information, you can see our wiki pages for these products, and we have YouTube videos on them as well. We have a store in Tindie where we sell all of our cards. Thanks for watching our video, and if you enjoyed it, don't forget to like, share, and subscribe.